important to me when we're doing this. Okay, so we've talked about work as from the definition, and just a reminder, that means that work was equal to F dot D. That's just what I'm talking about. This literally is what we did the page before. So this is like the force times the displacement times the cosine of the angle. Okay. And we talked about energy as the ability to do work. But one of the things that we really want to, the way I want you to think about work, is that it's in reference to the concept of transfer of energy. Work is how energy moves from being potential or stored energy into kinetic energy or something like that, where the work is literally the way energy moves from one thing to another. Okay, so in this, if we do positive work, work is a scalar, so direction doesn't matter. But if we do positive work on something, we are literally adding energy to that thing. If we do negative work on that thing, it literally means removing energy from that thing. I personally am a big fan of thinking about this with the idea of cars, okay, or something that you are familiar with, okay? If a car starts at rest and is pointed to the left, and its engine applies a force, what's it going to do? Literally, what is the car going to do? It's going to move left. It's going to, yeah, this is not a trick question, okay? I am not trying to trick you. I am trying to rely on your experience in the world and making this make sense. So it's going to experience a force to the left, and therefore it's going to end up having displacement to the left. It's also going to do what? Go faster, slower, same speed. It's going to speed up, right? If you're applying a force from the engine, we have minimal friction or zero friction. And so it's going to go from being at rest to moving. All right. So let me ask, what kind of work does this force do? Does it do positive work, negative work, zero work? Positive work, absolutely. The force and the displacement are in the same direction, so we can say that it does positive work. And I'm assuming in the depths of your mind, you still know that Newton's second law means F equals MA. Okay. Which also, net just means sum, which when we're dealing in forces, when we're dealing with vectors, we separate it into forwards minus backwards, or one direction minus the opposite direction. All right. Then, if you apply a force and there's an acceleration, back from the very first unit, we learned that if there's an acceleration, there's a displacement, there's going to be a change in velocity. Accelerations mean changes in velocity. So basically, would you agree that the car has added energy to it? Yes? And it's going faster. Okay. What kind of energy did it have added? Potential or kinetic? Kinetic. It went from being at rest to being in motion. It's, again, I'm not trying to trick you here. Okay? It's added kinetic energy. It's going faster. Okay? So this is telling us that there's a relationship between the work being done and the change in kinetic energy. On your next page, and we define kinetic energy as 1/2 mv squared. We did this already. Remind me, what are the units of kinetic energy? Joules, heard it. What are the units of mass? Kilograms, heard it. And velocity? Meters per second, heard. Awesome. Nice job. Okay. On the next page, top of the next page, it literally goes through this entire process. Am I expecting you to recreate this? Absolutely not. Am I trying to help you understand where this is coming from and what it is useful for? Yeah, that's the point of this. Okay, so we're going to start with the idea that force is equal to m times a. Does that sound familiar to everybody? Okay. And we know from kinematics that V final squared is equal to V initial squared plus 2a times the quantity x final minus x initial. Is that okay by everybody? All right. When we're talking about work, we've been replacing x final minus x initial with what letter? D, the displacement. Okay, so I'm putting that in there. So if I do a little rearranging to find the acceleration, I can say that I have v final squared minus v initial squared. That whole thing over 2d is equal to the acceleration. Now, I also have in here that work net would be the force net times d times the cosine of the angle in between them. To make things simple, let's assume that the F net and d are in the same direction. What will that make cosine of 0 then? That just becomes 1. Okay, so we just have F net. So I've got my work net is equal to F net times D. All right. So work net would be MA times D. What was my A? Okay, now this doesn't look somehow magically easier until I realize something, that I can do some rearranging and some distributing. So I'm going to do that. I'm going to say that my work net is equal to, I'm going to pull the divided by 2 out in front and make that a 1/2. So each thing is multiplied by half, and then I'm going to distribute the mass. Oh my goodness, what is this? Kinetic energy. We've got, and not just the kinetic energy, we've got 2 kinetic energy formulas, and they're in the order of final minus initial. So what does that mean? It's the change in kinetic energy. Okay, so this is the big takeaway, that we can relate the work to the final velocity. Okay, we can relate these two. This is the big deal. All right, we have enough time to get started on example problems, but we're not going to finish. So are you guys all cool if we start the example, what's called example problem number 2, which is somebody pushing a lawnmower? Okay, and then we will leave off before we get through the other stuff. So our next class, please be ready to do a whole bunch of practice problems in class. But what we do in class, ask questions about then, because I'm not going to come back to those again. Cool? All right. So we've got a man pushing a mower for 15 meters with a force of 11 newtons at an angle of 65 degrees above the horizontal, and assume that this is a frictionless surface. So basically, if I were to draw my mower, okay, when they're saying it's at 65 degrees above the horizontal, they're saying this angle right here is 65 degrees. Is that cool? Now, I am going to choose to not go backwards, but I'm going to draw in an axis here. And I'm doing this mostly so that I can be thinking about this whole thing ahead of time and then come back, and then I can come back later. So what are my forces? I've got gravity going down, I've got a normal force going up, and I've got this push. And this push is going, down and to the right, so it's going to be over here in the fourth quadrant. Okay. And it said it was 65 degrees above the horizontal. That means it's 65 degrees below the horizontal here as well. Okay. And below the horizontal, we just call that a negative 65. Right? Correct, I should say. Are we good with that? Okay. Which way is the displacement going to be? To the right. Absolutely. So this makes it relatively easy for me to say my work net is the sum of the works, which would be the work done by gravity plus the work done by the normal force plus the work done by the push. Now, the normal force and the displacement make what kind of angle? A 90-degree angle. They are perpendicular to each other. Gravity down and displacement right are perpendicular to each other. So if the force and the displacement are perpendicular, I'm going to literally just every time make a perpendicular symbol and say they're going to go and become zero. I can ignore them. I want to do that so that if there is a question of, do I get that they are going to effectively disappear, but they still count, that's important. So I can just say that the work net is the work of the push, which would simply be the force of the push times d times the cosine of the angle in between them. And from my handy dandy drawing, and the problem statement, I have that the force was 11 newtons, the displacement was 15 meters, and the angle is 65 degrees. So, would everybody do a quick punchy in their calculator for me? And what does that come out to be? It goes on and on and on. So the net work would be 69.7 joules. Okay. We've been doing that up to so far. Okay. And then the next question is to find the final velocity, which I'm planning on doing next class. All right. Thank you.